conference that happened this week. AppSec EU is coming up, I think, in May, so get that onto your boss's budget. Or if you're like me and there's no chance that you're going to be able to get there, make sure and check out the videos online that they post on YouTube and whatnot. In fact, AppSec Cali will probably have theirs posted soon as well. And then local news, like I said, we haven't had a meeting in a couple of months. Usually things get busy towards the end of the year with holidays. We try to shoot for the last Friday of the month, so usually that's Thanksgiving, Christmas, New Year's, whatever. So that just naturally happens, but we are looking at having monthly meetings for the foreseeable future. So look out for more information on that. Along the same lines, if you're interested in doing a talk or even hosting a meeting somewhere where you work, or an open space where we can meet to balance the load of the different groups. So it's very helpful in hosting the meetings for us, but we like to kind of change things up a bit and then make it easier for other folks that have to travel a long ways. Anyway, we're open to suggestions, open to talks. If you're looking at some of those AppSec conferences and you see a talk that you'd like to get more information on, or maybe even invite the speaker to come here, we can definitely try to facilitate that. So let us know if you have interest there, or if there's any subject matter that you'd like to see a talk on, we can see what we can do about that. So we're always open to feedback along those lines. So with that, today we've got Dan Cornell from the Denim Group to talk to us about integrating security and DevOps pipeline using some cool attack surface monitoring. Yeah.
All right. Welcome, everybody. Fantastic. A lot of people. I think all the chairs in Denver are currently being used right here. I'm not sure what everybody else is doing. Probably standing at their desks, which is supposed to be healthier. That's good. Yeah. So what I'm going to talk about today is some work that we've done that was originally started by research that we did, funded by the U.S. Department of Homeland Security, that we've gone and found some alternate use cases for. Specifically looking at application attack surface. And so if you look at a web application, for example, the attack surface is going to be the set of URLs that it will respond to and the set of parameters that you can pass in that can change the behavior of the application. If you think about a mobile application that's got a potentially more complicated attack surface, because it's maybe calling out to different things, you can pass, like an Android, you can pass intents in and things like that. But what we're going to look at for our purpose here today is our web application attack surface, and specifically watching that attack surface as it changes over time. And the reason, there's a number of reasons that you might be interested in doing that. And the specific one that we're going to look into today is if you want to integrate application security testing into your continuous integration, continuous delivery pipeline, a real challenge is the testing time associated with this. And a lot of kind of the current crop of security tools don't do well in those types of environments. And so what we're finding are there's some ways to use this attack surface to help you prioritize the type of testing that you're doing. So that's a quick summary, and probably echoes a lot of the agenda. That's a picture of me when I had a respectable haircut. RSA is coming up soon, so I will soon have another respectable haircut. My colleagues will probably choke me and not let me go. So we're going to look at doing some testing with Zap. Who here is familiar with OWASP Zap? Excellent. If you're not familiar with it, certainly check it out. It is both a web proxy and a dynamic application security assessment tool. Open source, and it's an OWASP project, and it's a pretty, if you look at the code base projects, it's probably the most active code project at OWASP. Simon Bennett works for Mozilla, and they pay for a chunk of his time to be dedicated to OWASP Zap. And it's got a great community around it and whatnot, and so it's a fantastic tool for learning, for integrating your pipelines and things like that. So we're going to do some examples with Zap. A lot of the dynamic testing tools these days are exposing APIs, and so you could in theory, and I've looked at this, so I know that you can for certain ones. You could do this with other dynamic testing tools, but for the sake of being able to replicate this stuff, all the examples we've got today are in Zap. There's a couple example code bases out there. Again, this is more just that you have links. These slides are posted online, and so we'll make sure to get these to everybody. But these are some example code bases you can use to test some of the stuff on. You can also pull from GitHub the ThreadFix Community Edition. all the stuff that we're talking about here today, you should be able to do from the stuff hosted on the GitHub. And we've also got downloads here of a couple of binaries if you don't want to go through all the trouble of building that on your own. So the goal here is to make all this, like everything we're talking about today, you should be able to go and replicate and do with a reasonable amount of effort. And again, we've got links in the slides. Okay, so attack surface. Why is attack surface important for application security? If you think about it, the attack surface is every way, every option that an attacker has to reach out and touch your application, or reach out and try to get your application do something that is going to be to their benefit. And so when you're scoping testing, it's important to understand, like, are we getting sufficient coverage of this application's attack surface? Right? If you're only covering 5 or 10% of the application's attack surface, well, that's a whole lot of additional attack area that hasn't been tested where you don't know much about the security state of that. And so, I think a lot about organizational attack surface with web applications or mobile applications. What is your organization's application portfolio? But this is even drawing that even in more closely to look at a specific application to say, let's look at that individual application's attack surface. And so, as I mentioned, for a web application, this is really the stuff that comes in HTTP requests. So it's the URL that they're hitting, get and post parameters, also cookies, headers, things like that. These are the options that an attacker has. This is the attack space that an attacker has, where they can try to get your application to do something that's going to not be in your best interest, or it's going to help them accomplish goals. If you look at mobile applications, IoT applications, those potentially have an even more complicated attack surface just because you have different components that are talking to one another. Again, as your threat model increases, understanding attack surface becomes more challenging. For today's purposes, we're going to focus on the web, but there's no reason that you couldn't take what we're doing with web attack surface and extend the type of parsing and stuff that we're doing to also, for example, like look at an Android application, and like I said before, you can enumerate all the intents, but also look for cases where it's calling a database, pulling files in, and things like that. And so, I think what we're doing here could certainly be extended, to other types of applications. And also today we're going to be looking at dynamic testing, right? And how you can use some of this attack surface knowledge to impact or to guide your dynamic testing. Both for automated dynamic application security testing as well as potentially manual assessments or penetration testing. So what does attack surface have to do with DevOps? If you want to get your talking step into conference these days, it has to have DevOps in the title. Another option is IoT. No. What we've been spending a lot of time with organizations looking at, what does it mean to, as an organization moves to DevOps, how does that change the practices they have? Because as we see in most organizations, it's not, like security might not like the idea of moving to DevOps, but the business and the development organizations are going to do that. They want the reduce costs, they want to increase agility. The business is going to do this whether or not security signs off on it. And so it is critical for security to understand, like, how do we stay relevant? How do we remain part of the conversation? And so we've been doing a lot of work, both kind of at a higher policy level, but also at a technical implementation level, looking to see, how does security, and in our case, most specifically application security, how do they stay relevant? How do they stay involved in this conversation so that they can influence what the DevOps teams are doing? And as we'll see, challenges with testing often are that testing takes too long, right? Like traditional security tools are going to take too long to run inside of what a development organization thinks of as, how long their pipeline should be running. And so what we're going to do is look at how playing with attack surface allows us to potentially do some different stuff, or to optimize our testing so that we can get security insight into the state of the application as it changes. It might not be as exhaustive as you would want from full analysis, but we're going to look at those trade-offs. And again, that's the challenge with security: is what are the trade-offs? How do you stay relevant? And how do you get the most benefit for the effort, for the resources you're allowed to consume? And we've seen organizations, Etsy, Netflix, those organizations are at one end of the spectrum, where I think at Netflix, every time anybody presses a key on a laptop, like they just deploy all the, code goes out to the new servers or something, those organizations kind of made a lot of noise about, and have really shown the industry, hey, this is how fast you can aspire to deliver software. If you work at a bank, I don't necessarily know that you need to be able to deliver new software at quite the speed that those organizations do or that they claim to. But that certainly has, if you look at organizations that are adopting these practices, they've really changed the perception of what does a cycle look like to, from when I write code to when that code actually lives in production. And I think every industry has value that they can extract from the types of practices these organizations are adopting. And so when we look at security testing in a DevOps pipeline, we see that, specifically application security testing, and I've got a link to a blog post that talks about this in more detail, but we look at three phases that occur. The first, there's the testing phase. That's where you're going to perform some sort of checks with the goal being to get additional security insight into this application. And a real challenge here is some of the testing that you do, you may want to be synchronous, right? So you want to wait for the results of that testing before you make a go or no go decision on the pipeline. The challenge is that for most dev teams, they're not going to want you to kick off a 4-hour Fortify scan, right, or a 2-hour app scan, right? That's not acceptably, that time frame is not acceptable to get a thumbs up or thumbs down decision, if you're looking at the type of testing you might be doing after every commit. And so you also have to think of asynchronous tests that might be kicked off, as part of this process, but where you're not going to have the luxury of waiting for the results of that coming back in before application security gets to weigh in and say, yes, this build can pass, or no, it can't. And so when you're running tests asynchronously, you've got to have something in place that's going to catch those errors and mop them up before. And so for security purists, I think this could be potentially concerning, because you're saying, well, you mean it's acceptable to pass a build that has, that we ultimately find has security vulnerabilities and put it in production. We don't want to put vulnerable code in production. To that I ask, well, with the annual pen test that you're doing right now, do you think you don't put anything into production, without vulnerabilities in it? And so, I think even if you're looking at a situation where you may pass something through a pipeline and deploy code that has vulnerabilities, being able to deploy new code quickly and having a process in place to detect these so that you can shrink that window of exposure, that actually creates a lot of value. And so it's scary to me as a security person to realize that code with known vulnerabilities may find its way out into production. But as a developer, the reality is, hey, this stuff's going to get shipped. And before you started doing this type of application security testing, you didn't have any insights. You didn't even know. You can't quantify the impact and make decisions about it. So when you look at doing testing, application security testing in a pipeline, there's the both synchronous and asynchronous tests. Then you make a decision: do we want to pass this build or not? And so you're taking the results of this testing to determine, are we going to weigh in as the voice of the application security and say this build is not allowed to move farther down the pipeline? And in a perfect world, you could have policies that said, no critical and high vulnerabilities. We're never going to pass a build if we have any known critical and high vulnerabilities, right? That would be nice and probably works great in the perfect world. But if you look from a practical standpoint, when we go and work with organizations, that's not necessarily something that that application security is politically going to be able to do. Right? If you've got an application that's got 1 million lines of code, you have run scans in the past, and you've got 1,600 cross-site scripting vulnerabilities floating around out there. Guess what? You're not going to get to break the build for 3 months until all those get fixed. Right? That's simply politically not going to be possible. And so when you're making decisions from a policy standpoint, you may be able to, you might not be able to say no criticals or highs, but it may be much more politically defensible to say no new criticals and highs, right? So that way you're always kind of monotonically decreasing the exposure you have from the vulnerabilities that are out there. That's an argument that you're in a much better position to win than taking a hardline position of never pass something if it has these types of vulnerabilities. And so that's something that, and again, what we've seen in a lot of these cases is you really have to make tough trade-off decisions, which is, they're tough decisions, so it's obviously challenging. But that's the price you pay for getting a seat at the table, which I would argue that a seat at the table as organizations start to craft their DevOps organizations and the policies around it, that's much more valuable than taking a purist approach. Finally, then you need to report what was found. And so we'll look at some examples from ChatOps, which is fancy IRC with like better GIFs or something these days. I'm not sure. But also a lot of times this means reporting out to Jira, to Bugzilla, whatever defect tracking or application lifecycle management system is in use. And so again, we're going to do some testing. For the tests that we had the ability to wait for, we're going to make a decision, and then we're going to report the results of that out. And so at a high level, that's kind of how we view application security testing integrated into a DevOps pipeline. Any question on that so far? Fantastic. So the practical challenge, or a real practical challenge that we've seen looking at this, is that a lot of the security tools simply run too long to include in the pipeline builds. When we talk with organizations looking at these types of rollouts, they get a budget of 8 minutes, 10 minutes, 12 minutes is the time budget. If you look at like a per commit check-in or a per commit job that's going to run, that's what we've heard from talking to customers about what the time allocated to application security where they can weigh in and make a decision, right? I don't know. I haven't seen. You guys may have different experience. I haven't seen a lot of 4 to 5 scans that finish in 8 to 12 minutes of non-trivial applications, right? Maybe if you got a really fast laptop or something, right? And so traditional security tools can be challenging to fit into this pipeline. And also automation can't catch everything. And so if you look at manual testing, that's simply incompatible with integrating in a synchronous way into pipeline, unless you've just got a basement full of folks that are ready to manually pen test the crap out of stuff when new builds are available. But it's important to understand, well, how are we going to accommodate these requirements that we have, but within the constraints? So what we're going to look at here is how, if you track, or by tracking attack surface changes over time, that puts you in a situation where you can focus testing activities to say, I only want to test the stuff that I consider to be high risk or that is going to provide me with the most benefit, as well as its trigger testing activities. Again, with things like manual testing, hey, we know we can't do this every time, but let's watch as the attack surface changes, and maybe we can use that. After we see that the attack surface has changed by a certain degree, that's when we decide that we want to initiate some sort of testing. So those are the types of things that we've been looking at and that I'll be talking about here today. So the underlying technology that we're going to be looking at is a technology called hybrid analysis mapping. And it was originally created so that we could basically dedupe and mesh the results of static application security testing and dynamic application security testing. Folks that have been to OWASP San Antonio, this is something I've talked about a couple times along the way, this technology. So I don't want to get too mired into this, and I've got slides in here if you want to read more about what we did. But the original goal was the research that was funded by the Department of Homeland Security was to integrate or to dedupe the results of static testing and dynamic testing. And what we found after we built this technology is the way that we built it, there were other things that we could do with it that in certain for certain applications, especially what we're looking at here, is potentially more interesting. And so. Let's see. This is funded by the DHS, Department of Homeland Security, Science and Technology Directorate, Cybersecurity Division, under the SBIR, or Small Business Innovation Research contract or program. Which again, federal agencies, what they do is they'll say, "Hey, here are technologies that we feel like we could use to accomplish our mission. Does anybody have proposals on how to do this?" And so we basically put together a proposal and said, here's how we think this would work, here's how we commercialize the technology. And so for the past 2 or 3 years we've been in this program, and I've got nothing but good things to say about it. One thing I will say is, please don't assume that the talk is endorsed by DHS. This is me talking about what we've done. DHS funded the research. What we do with it, good or bad, is kind of on us. And so this is not endorsed. Hasn't been through their approval people or any nonsense like that. And so again, the original goal was, how do we dedupe the results of static and dynamic application security testing? And we'll look at other stuff we did with the technology. Here's some of this stuff. And originally we were focused on Fortify static and AppScan dynamic. Just that was the market need that we saw the most of at that point in time. But the way that we did it is independent of the of the underlying SAST or DAST engines. So is everybody here familiar with dynamic application security testing? All right, so you point something at an application and you spider it, much like Google would. You probably have to have, for non-trivial apps, you've got to have some login capability as well as state detection to determine, so that you can crawl the entire application and not just the home page. Then once you've identified this attack surface by crawling, so grab the HTML, grab the JavaScript, look for links, look for forms and submissions and things like that. Okay, go on to the next one, go on to the next one until we've crawled all of that. Now we have a picture of the application's attack surface that we've organically built by crawling. Then we go and do directed fuzzing. For each parameter that I can pass in, SQL control characters. If you get a SQL error message back, that is that request and response pattern indicates the presence of a SQL injection vulnerability. And for us, a unique finding like that looks like the vulnerability type. We use the MITRE CWE just because it's the it's the democracy of vulnerability taxonomies. It's the worst one except for all the other ones that people put together. And the nice thing is, like, a lot of the tools and things have mappings to it. So we use MITRE CWE, the relative URL, and for certain classes of vulnerabilities, the injection point. And so if you think of like a reflected cross-site scripting vulnerability, you would have in login.jsp for the username parameter or for the password parameter. For other things, which is like, hey, you have like a bad Apache configuration that shows directory listings, that's just going to have the vulnerability type as well as the URL. It's not going to have any additional entry point information on top of that. For static application security testing, we're going to take the application source or the application binary, build a model, do some analysis to build a model, and then run through and do data flow analysis, control flow analysis, semantic analysis, and in that case, our finding looks like the vulnerability type and then the data or code flow through the application. And so here we see we're calling get parameter, which is this value is under the control of a potential bad guy. That gets assigned to the username string, which is then considered tainted. That tainted string gets appended in with some static text and assigned to the string SQL, which is then also considered tainted. Then that gets passed into this sensitive function of execute. So it's kind of a textbook example of a SQL injection vulnerability. Similar, so we're finding the same types of vulnerabilities, but with different types of analysis. Rather than sending in a request and analyzing the response, we're checking the data flow through the application. All right, same vulnerability found by different techniques. And so, from that, we basically standardized the vulnerability types across scanners and things of that nature. But the real challenge that we had in doing this is to figure out how do we map between the source code or binary code artifacts of the application and the behavior that code is going to have when it runs, right? That's really the challenge that we're looking at, is how do we look at, how do we translate between the code for the application and that application's ultimate behavior that's going to be experienced by, as network request comes in and they have to respond. And so, we had to figure out how do we map between a URL on the dynamic side, where we're seeing behavior, how do we map that back to the code that was responsible for exposing that URL? And when we are taking parameters in, similarly, we have to figure out if someone changes or when they pass in this certain parameter, where does that enter the source code to then make its way through? So basically, we take in the source code of the application, detect the language in the framework, and from that, we build this database. We call the unified endpoint database, and that basically says, for this URL and for this parameter, here's the entry point into the source code that's responsible for that behavior in the application. So to merge static and dynamic results, once you've gotten to this point, it's easy. Which getting to this point was not super easy. But if I have a dynamic result, right, that says I have a reflected cross-site scripting vulnerability, and it enters the when it happens, or I can exploit it when I send a request to login.jsp and manipulate the username parameter. If I feed that to my endpoint database, it's going to kick back and say, well, this is a Java Spring application, that's in combat whatever login controller.java line 62. Right? Then I can go and look at my set of static results to see, do I have any reflected cross-site scripting vulnerabilities where the source function in the source code is that login controller.java at line 62. If I do, I can stitch those together and say, I believe I have one vulnerability that I have two pieces of evidence about, instead of this being two independent findings. And so again, once you've built up these data structures, that match is fairly straightforward. Any questions about any of that so far? Excellent. So we were happy because we were able to do what we wanted to do, but that led us to ask the question of, like, what else can we do with this technology? Or once we've built these data structures and have the ability to do these queries, what does that, what else can we do with that? And that's, again, one of the cool things is kind of an editorial on the SIBR program. It was cool to me, hopefully to our program manager, but it was cool to me that we set out to solve one problem, we were able to do that, but as we'll see, we were able to use this underlying technology to do other stuff, which is kind of a neat thing about research is you don't necessarily end up where you thought you did. So what other types of things can we do with this? Well, if I have an entire attack surface model of the application, I can take that model and hand it off to something like a dynamic scanner. So instead of that dynamic scanner having to start at page 1, crawl to page 2, crawl to page 3, check to make sure it's logged in, right? Instead of having to discover or guess at what the application attack surface is, if I know what the attack surface is, I can just feed that to the dynamic scanner, and it can start its analysis from that point. And so if there are things like hidden landing pages that link into the application but nothing ever links out to them, if there are like hidden or debug parameters that you would, again, these are things you would not see in the HTML or in the JavaScript, but the application will have those behaviors. That's valuable for us to know because that's going to allow us to do better scanning. Again, this is just kind of if you want to replicate this stuff. If you've got a run thread fix, you can download these tools. Also had links posted where you can just pull them down directly. So what we've done is we built plugins for Burp and Zap, and I think we have AppScan, but I don't know if it is publicly available yet. So we have plugins that you can use that basically will do this type of analysis and let you start your testing from that point. And so again, this attack surface enumeration lets us figure out all the URLs that the application will respond to, all the parameters that you can pass in to change the behavior of the application. So a really interesting thing, like the worst case where this would have been valuable that I ever found was a Cold Fusion application where if you passed in a parameter named D to any page, whatever the value of that parameter was, let's say I passed in D equals 1000, it would go find order number 1000 and delete it, right? It's like a convenience function. I don't think it was a deliberate backdoor. I think it was something that the developer put into that code so that they could easily go in and delete functions. And since it's Cold Fusion, it got cut and pasted to the entire thing. But that's a type of information as a penetration tester that I would be very interested to know about. And so that's those are kind of the scenarios where we see this as being valuable, that type of seeding. It's also really handy if you've got mobile applications that are talking into REST APIs, because you can enumerate all of that REST API. And so if you think from a mobile application assessment standpoint, kind of the typical behavior or whatever is to take your mobile application, proxy it through Burp or Zap or something like that, exercise the application and see what calls get made. That's great, but just because you've got a set of calls that you see that are being made, that doesn't mean that those are all the calls that were exposed. And so there may be debug functionality, other stuff, things that you didn't get to because you didn't have the rights to. And so again, by being able to enumerate this API attack surface, that gives you a better starting point for doing for doing testing. So the benefits of this, obviously you can reduce false negatives. If you're fuzzing more of the application, or if you're not failing to fuzz parts of the application, you're going to have fewer false negatives because you're testing more of the application. And again, if you're doing manual testing, again, that allows you to have more confidence that you're pen testing all of the application. Those are some handy notes. And so I'll show you a demo of kind of what this looks like. Close to me, of a size that people can read. Good? Good. All right. Okay, good. And so one of the things that we did with this technology is just basically a command line client. And what the command line client does, you point it at some source code, it builds a model, and then just dumps it out to the to standard out. And so whatever. And so if we look at So there's a test application called Budget, which is an intentionally flawed storefront. So we point it at the source code, it detects like, okay, hey, this is a Java JSP application, and it dumps out a list of all the various all the various URLs and the endpoints. And since these are JSPs, you can pass they'll respond to both the post and gets. But what we find here is some interesting stuff. Like we find that this page here, admin.jsp, if we're doing an unauthenticated crawl, that may never be a page that we would know anything about. Just as we crawled the application, because we may never have any links rendered to that. Also, you'll notice there are a number of these parameters called debug. What are those? I don't know. But if I'm a pen tester, that's very interesting to me to say, a parameter called debug. Is that something that we're going to see in the HTML and the JavaScript? Maybe not. And so, so from a manual pen testing standpoint, this lets me have a good punch list of, hey, I need to make sure that I've covered everything. And furthermore, we've seen some interesting stuff here, that may merit further attention. If you look at Rails Goat, what we do with Java Spring and Ruby on Rails is we'll parse the model classes and look to see how those get stitched together. And so what you see here are situations where when you pass into account settings, you can set things like you can set, if you put these periods in between, you can actually walk down the object tree and set things farther down in the object tree for when the request gets passed in. And so you can identify these so-called auto-binding errors, or at least potential for auto-binding errors, by running and looking at the parameters to say, and these aren't like really damning examples, but you can see sometimes stuff where it's like something dot something dot something dot something. And it's like, oh wait a minute, like is this really supposed to be set up like that, or should the configuration have limited how deep you can go into this stuff? Any questions about what we're doing here? Excellent. And we also have the ability to dump this output as JSON, which is kind of forms the stuff that will, forms the basis for a lot of the stuff that we're doing later. Where we've got the file path, we've got the line of code, we've got the parameters that are passed in, so on and so forth. And so we can dump this out in a structured way. This is a Java library, so you can, if you're writing in Java, you can just include this and build this model and do stuff with it. And I've also got example code where you can call it from Jython as well. I've tested it. I've always thought that should work, and it does. So if you want to write in Python, if you want to write in Java, I don't know why it wouldn't work with JRuby or any of those other kind. We're not using any weirdo APIs that it's just like file reading and stuff like that. So if you have another thing that runs in a Java VM, you ought to be able to use this library and manipulate it. Okay. Let's see. Any questions about that so far? Okay, so now we can look at seeding a scanner. So let's see if I have Zap running. Yeah, so we've got Zap running here. We've got a running version of Logic going over here. So this is a standard Zap scan. We go and say import the endpoints from the source code. That's where the source code is located. That's where the thing is. And so what we see is that, again, we've got links to this admin.jsp, to the various things that have the debug parameters. And so our starting point for doing this scan with Zap is is that we have this additional attack surface that's in there. And also the way that the plugin works, it also hooks Zap's API and exposes those capabilities. So if you wanted to script the seeding of the scanner and stuff like that, you can do that type of stuff as well. Okay. So that's kind of looking statically at attack surface, which again I would argue is interesting and valuable. What we're going to talk about from here, I also have a warning. This is actually from a big bank that we're doing a thread fix deployment for. I was describing some of this to them and seeing how this fits into their plans, and our contact over there said, and this functionality is currently available in the crappy form of code that you produce, right, Dan? Which is true. Eventually, this gets turned over to the thread fix engineering team, who are actual professionals. But the stuff that we're looking at here today was written by me. So what's the opposite of Pythonic? All right, Pythonic is supposed to be like if you you kind of follow the style of Python and whatnot. I'm a horrible Python programmer. What's that?
Moronic?
Moronic, that is entirely possible. There's probably some there's some sloppy file handling, race conditions. There's probably some command injections that you could inject from the command line, so that's not really a big win. But I would not, for example, open an unauthenticated web server and pipe the results of a request into this code. I wouldn't attach it to the network. Again, if you're running from the command line, not an issue. But this is stuff that is evolving over time. And so what does this live do? Basically, it manipulates the output of these of that endpoint CLI. So when you dump out, it basically runs that CLI, pulls the JSON, and does stuff with it. For some reason, I wrote all this I wrote wrappers and then wrote all this in Python. And then last weekend, figured out that I could just call it from Jython. So I did that maybe in the wrong order, but whatever. And also we do some get utility tests. And so this is kind of the basis for a bunch of the upcoming examples, but it's a wrapper library that makes it easy to kind of pull the stuff in and manipulate that. One thing that we can do that is not that interesting, or at least that I don't want to spend a tremendous amount of time on, but is you can start to do visualization to say, well, what is the directory structure, what is the URL structure, what do the parameters look like for these for these applications? That's again potentially interesting. Although it gets really hairy with bigger applications, you can also look at this stuff side by side to see what stuff has changed, what stuff is added. If we have two different versions of the application, how have things changed? There's probably a lot of cool work to be done on the visualization. I'm not a person to be doing a lot of visualization work because I'm bad at it. But if we can get this data in a structured format, then we can start to do some interesting stuff. So let's see what we can do here. So if we look at budget across two different versions, and just so I've got basically a couple scripts that call into that other script. You pointed at a Git repo, give it the start commit and an end commit, and what it's going to do is it's going to build attack surface models for those two different applications, and it's going to run a diff of those data structures and then talk about the stuff that came out of that. So what we see is the differences between commits whatever are that we've added the attack surface of these 4 pages. We haven't deleted any, and we do some calculations on the percent. What percentage of the attack surface has changed. And the reason that I've been messing around with doing the percentage calculations is, you can look and see, we talked before about doing things like manual tests and whatnot. Maybe your policy is, hey, we're going to do manual testing every time 20 new URLs show up, right? Or every time the attack surface has increased or decreased by 10% or 15%, right? That's still an area where we're kind of playing around with to find out what makes sense there. But again, by looking at this attack surface and figuring out how does this fit into a policy framework, those are the types of questions that you can potentially answer. So to look at a more complicated application, this is running the attack surface of thread fix between a somewhat recent commit and one from a couple years ago. It takes a little bit longer to run, but if you'll notice, and thread fix is 100,000 lines of code or something like that. So that we just did our attack surface modeling twice in the time that it took that to run, and so the runtime for this analysis, the parsing that we're doing, is real simple string tokenizing stuff, running some regexes against things, and so this isn't like we're doing a full data flow or control flow analysis where it's going to kick off and grind on stuff for 4 hours or whatever. This runs pretty quick against even decent-sized code bases. Again, just because the processing it's doing is fairly straightforward. And so what we see here is that we've got added attack surface, a whole lot of stuff, but we also have some deleted attack surface. And that's probably over time as features moved around in the applications and whatnot. And so again, from this we can look to see between these two different versions of the application. All right, here's how that application has changed over time. what we also, a question that came out of the presentation that I gave, or when I gave this presentation earlier in the week at AppSec Cali was, well, so we know we can find out what's added and what's been deleted. Can we also make a guess as to an attack surface whose behavior may have changed, right? And so what we did is said, okay, well, I can look between these two Git commits. I can find all the files that have been modified, and then I can find all the URLs that are associated with those files that have been modified. And so we can calculate what may have changed, right? And so, like, to be more specific or more correct, again, you would have to look to see, well, I mean, there could be, like, you know, when files call between files, you know, an intermediate file could have been, could have been changed. And so there's the potential that we're going to miss URLs whose behavior may have changed by doing that type of analysis. And similarly, you can make changes to, like, part of one file, but that's not, you know, even associated with the code that's going to run. And so there's the possibility for both false positives and false negatives if we're trying to detect what behavior has changed. But by doing that analysis, we can at least at a rough level make that type of calculation. And so here we see is that we've added a bunch of stuff. This is from a really old commit. We've added a whole bunch of things, haven't deleted any things, but we've also modified along the way a lot of this attack surface. And so so that gives us different thresholds that we can look at for potentially taking action, right? We can say, well, I want to pay special attention to new stuff because I know it's new and it's never been looked at before. If you have more time, maybe you would also then like to look at stuff where there is a high chance that its behavior has changed. But again, by having this data available to you, you can start to figure out how, what's going to work from my time constraints and my other constraints, what's going to work in our environment. Because again, things maybe for one application may be acceptable, for another it may not. Also depending on how large the commits are that people are pushing in and whatnot. So any questions about any of that stuff so far?
Is that all included in the endpoint CLI, or is this code?
So this is because I can't do anything the straightforward way. This is Python running on top of the CLI, so it shells out to the CLI. You could certainly, if you're writing in Jython, you could just import, and I've got an example of this, you can just import the library and do it in Python code, okay, which would have been the smart way to do that. Or if you need to use Python stuff that you can't run in Jython, then this way it works. It's just a little bit gross because you say point at the source code at a certain point in time, make this gradually dump this JSON into a file, read the file in, turn that back into actual JSON, and basically doing things the exact hardest way.
So you're just post-processing the endpoint CLI output.
Exactly. Yeah, and this is also the exact same JSON that you would get from the thread-fix server REST API endpoints as well. And so, again, you could, if you had a situation so in one environment that we're working in, the testing team can't have access to source code directly, but the thread-fix installation does have access to source code. And so we've got the thread-fix talks to the source code thing, does the attack surface analysis, and then feeds that over an API to the testers who can use it from there. Because I'm not the only one that has to do everything the hardest way possible. Excellent.
So is this available in the community or the one that's listed on?
Yeah, all this stuff should be available from the community edition stuff. There's probably we need to do some updates to that, and we also have a contract with the DHS that is going to provide for some ongoing maintenance of the community edition that we're almost in a state where we can publicly announce, just because it takes longer than you want it to. So there's a little bit of cruft and stuff around the community edition stuff, but all the stuff should work, and if it doesn't, let me know and I'll kind of slap it around and make it work. But yeah, all this stuff is again it should be available from the GitHub stuff. Okay, so when we talk about chat ops, who thinks chat ops is cool? All right, good, a couple people. It's interesting to me also to look at, to keep things on developers' mind, to understand hey, developer, you checked in this code, that's going to change this behavior of the application. And so one of the things we've looked at is to watch the source code as it changes and to notify the developers when interesting things occur. So for example, we could say, I want to watch this source code base, and when new attack surface shows up, I want to report to the team, hey, this commit introduced new attack surface. Okay. So if we are in this version of Budget and we copy the search page to search 21.jsp, git, and a super helpful commit message. Right, and then when we push this, so that pushes that out to junk repository GitHub. We pick that up on the other end, calculate to see if there is a difference in the attack surface, and then we say, like, hey, what we notice is that we just had search 21 got added to this application's attack surface, which is conveniently, we can see over here in Slack, this notifies and says, like, hey guys, by the way, this commit just changed the behavior of the application in such a way that it's, that you may want to care about that. So that's all well and good. What we also may want to do, another thing that we might want to do, another thing that we may want to do is to say, hey, when we get a new commit in, let me just get a new zap so it behaves itself, hopefully. After restart, there we go. Okay. If we did that same thing where we're going to monitor this application, what we can also do is say, for example, so let's copy search.jsp to what I did last time, search 21. JSP. Another helpful error or helpful commit message. So what we can also do is potentially say, hey, if I know that certain URLs have changed, let's run tests where we only check the new URLs, right? The new URLs in the application. Is that as good as? So we see that Zap is getting kicked off here. So what we're doing is we're doing a Zap test, but only of that new search22.jsp that was introduced based on that commit. Is that as good as doing a full end-to-end scan of the application? No. Is it better to do scans of new URLs rather than doing nothing? I would argue yes, right? And so we saw here is when we checked in this new search page, we ran a Zap scan. We found that it introduced a cross-site scripting vulnerability. It reports that out to Slack and HitChat or whatever. And potentially that's a decision that you could use to break the build to say, hey guys, we know that we've got some existing cross-site scripting stuff, but you can't introduce new ones, right? Or we know that we've got some existing critical or high vulnerabilities, but you can't introduce new ones. And so by being able to use this application attack surface and watch it as it changes over time, that lets us shift our testing strategy so that we can get more frequent, it just sort of becomes practical to do more frequent application security testing, rather than us waiting 2 weeks or something, doing something at the end of the sprint or whatever else that might be. This is also something that can be useful looking at manual testing, or if you look at doing testing across sprints. Ideally, if you're in an agile environment, you want to do some manual testing. Again, the developers would be able to tell you, well, we implemented this feature and here's the stuff associated with it. But developers are all horrible liars. And I know because I am one, right? And I'm forgetful, right? What this lets you do is, it gives you the ability to do some analysis of the code and to determine that information on your own, right? So you can see what's the, between the last time we looked at this and now, what's the stuff that is new, that nobody ever should have tested this, or it's likely no one has ever tested this, and what is the stuff that may have been modified. Let me focus my testing efforts there, because those are the areas that are at the highest risk for introducing new vulnerabilities. Also, just to prove that I can do this, or that we can do this, and we can run this in Python, which is how I probably should have done this from the start. There we go. And so basically what the Python example does is basically just recreates the command output of the command line client. But again, so now if you have other, if you have languages that will run in a VM, it should be possible to hook this stuff in. So if you want to talk to it from Scala, JRuby, Python, and so on and so forth. So if your language of choice in your environment is not Java, which is fine, you have the ability to access this technology and manipulate it from there. Okay, and that's it. And so I can run through these, but basically we've talked through all this stuff. And so again, by watching the application attack surface, that lets us kind of shape our testing strategy. Potentially test fewer things. That allows us to test more frequently, to notify developers about about the impact of their changes. Again, now that we're quantifying how the application attack surface changes over time, we can start to look at things to say, hey, every 20 URLs or every 15% of additional attack surface, that gives us more information at our disposal that we can use to test out policies, to go look at historical data to say, on average, how much attack surface do we add per month. This gives you the ability to start looking at additional stuff and to find new measurements that may be of value. That's that. You can also create JIRA tickets. That's not as fun. So the stuff that we're working on now, and really for there's the question really, or the challenging question that we're working through with folks now is, okay, so this gives us some additional capabilities, right? It gives us some additional stuff that we can do, or additional data we can use to drive decisions. What's going to be acceptable in these environments, and what's going to provide value. As I talked about before, if you look at a traditional run of a security tool, you could be looking at multiple hours that it's going to take to chew through that type of testing. That's not going to be acceptable in a lot of scenarios. And again, kind of anecdotally, or from working with different organizations, it's like 8 to 12 minutes is the app security budget that we've seen come out of a number of the organizations that are doing thread fix implementations. And so it's okay, cool. Well, I can go to war and demand that I need 2.5 hours to do a full regression run, or I can figure out what's the most value I can extract from that 8 to 12 minute budget that I've been given as application security to weigh in on things like this. And that's at the end of the day, I'm a big proponent of moving security left, and of putting development teams in a position where they can make meaningful use of security tools. And I think, again, by looking at opportunities to get these runtimes down, that puts you in a situation where these tools can start providing value to a lot more people in the organization, and can start providing value a lot more frequently and farther left in the process. Which at the end of the day are going to be good things. And being able to go, as a security person, being able to go to dev teams and say, hey, we're going to give you tools, but they're going to work the way that you want them to. We're going to make it so it's painless to run them really frequently. We're going to make it so it's painless to run them really early, right? That's only going to increase security's ability to influence the behavior of the DevOps teams as they roll forward. Any questions? I've been so clear and concise that no one has any questions. Yes?
So you mentioned that this can be integrated with Jira or Slack, and you can create tickets and you can notify the test team over there. But this this brings in the manual testing phase of it. But how does your solution affect automated tests or unit test cases?
It doesn't. I've seen some. So for unit test cases, no, like those would typically. I'm not a huge fan of unit tests to implement security stuff, just because most of the time when I've seen that done, it's like, here's a SQL injection, here's a unit test for SQL injection. I'm like, no, the better way to check for SQL injection is static or dynamic analysis, not like individual unit tests. So the unit tests are typically used, like if you look at the whole DevOps stack or whatever, the unit tests we see most frequently being used for, I wrote code, or I changed code, do I, at a module level, is this still behaving the way that I expected it would, right? And so these would be, again, those are going to be run probably by the developers, probably on every build, and so, this is really looking to say, can we get additional coverage or coverage of additional security risks that we're associated with? Can we use something like this to get broader coverage? So if you look at like what the pipeline is supposed to do, is you're supposed to like dump a bunch of code in the beginning of the pipeline, and at the end of the pipeline comes out some code and binaries or whatever, but also a decision that says it is acceptable or not acceptable to deploy this code, right? And so the unit tests are typically there to provide coverage to say, again, at the module level, has anything broken for the assumptions that we have about this stuff? What this does is this augments the type of testing that you can do so that it will answer the question, for new attack surface that I expose as a result of this commit, are there any really gross SQL injection or cross-site scripting vulnerabilities hanging off of that, right? And so it's kind of like stacking up bricks or whatever to make a wall, or like just trying to see like what kind of coverage can we get about the concerns that we have. And so this is, the goal with this is to augment the coverage of concerns that you can get, but within a responsible or a reasonable build time, within a pipeline.
So you pulled the endpoints out, which is good for dynamic testing. Are you also doing like what files have changed in the source code? So those are the ones we want to go back and scan.
Yeah, and so that you can do. I actually do that to calculate the modified stuff, but that's just, Git stuff. Yes, and we've been doing that. Wait, what's that? Yeah, that's not hard enough to be fun. No, and we've done that for a long time, which is, okay, well, hey, this code drop is here, this code drop is here. Let's look at the files that have diff between those. And again, that can guide if you're doing manual, code review. On the commercial providers, the only one that I know that does this right now is Checkmarx, where you can actually feed it like a second set of code, and it will like diff the ASTs between them and like figure out what paths have changed. So you can actually do differential runs, which is a pretty cool capability on their side, on the commercial side. But yeah, certainly, if you want to look and say, here's where the code used to be, here's where the code is now, you can get the files that have changed, from the source control system, as well as the diffs, and use those, and focus in on those. And that's the type of stuff that we do with when we've got applications that we assess like over time. That's what we always want to be able to do, because and again, especially you're looking from an attack surface standpoint, or from an outside-in standpoint, you could change a million lines and not change the attack surface and introduce a whole bunch of vulnerabilities or not, or you could change one line and like radically impact the attack surface, right? And so what we're really trying to figure out is like with the bell curve of like what's the correlation between changes in the code, changes in the attack surface, and the risk that new vulnerabilities have been introduced by that change. And how can we optimize our testing activities to give us the highest likelihood of finding those? And it kind of sucks because there's not a perfect answer other than like redo all the testing that you might do from the start. But again, I think by looking at the code that has changed, looking at the attack surface, the behavior that has changed, you can start to make decent guesses as to, hey, if I've only gotten this much time, either human time or machine time to do some analysis, here's where I want to look, because this is the most likely place. If there is a problem, this is the most likely place to check to kick up and identify that problem.
And then the Burp plugin or any other plugins that you have, they depend on the ThreatFix API? No,
so you can, with the plugins, they can either pull data from the ThreatFix API, which is fine, but it's kind of a pain from a configuration standpoint. If you have access to the source, it'll also, with both Burp and Zap, since they're written in Java, the plugins are written in Java, and you can just point at a local copy of the source code. And that's from a demo standpoint, or from like, again, we've seen at least one situation where just for like segmentation of access to whatever, you're like, well, ThreadFix can talk to source code, but testers can't look at source code, but testers can talk to ThreadFix, and we're like, okay, we're going to take the source code, stuff it in ThreadFix, make the attack surface model, send it over to REST call, and yeah, cool. Yeah, life in the big city. So, cool. Yes.
So I just want to clarify and make sure I understand what you demoed. So you go through and you're effectively just saying what of the attack surface changed, and if it changed, you can make decisions, say just run just this particular change through some dynamic testing.
Right.
But you're not, at this point, able to look and say, for the attack surface that previously existed, these are what was modified, so you want to go and look at these particular entry points.
So yeah, we can do that. We make a guess at that.
Okay.
And that's where, let's see where the
So there's, I put this calc modified.
So
Wow.
yeah, so we can do that there, but again, the way that we're doing that is we're basically taking from the source control system. It's saying here's all the files that have changed between those two commits, right? So we make that into a list of unique whatevers. On the attack surface side, we have a list of essentially a list of this file and this line is responsible for this attack surface. So we squish that down into a dictionary that basically says, like, here's all the files that are associated with attack surface, and for each file, here's a list of URLs. And then so we basically just, in like one line of Magic Python, like squish those together to say, for each file that has changed, let's see which, if any, URLs were associated with that. And that's what makes that list. All right, and so where that analysis is weak from a where it will miss stuff that had changed, it would be if the attack surface, like this file is responsible for the attack surface, but the vulnerability goes through that file, through another file that we don't know is associated with the attack surface, and then on to other stuff. All right, so that may cause us to miss situations where things have changed, where I would want to do that testing. Where we would miss on the other side and over report URLs is, hey, this file is associated with one or more URLs in the attack surface, but the part of the file that we changed is like a utility function that actually isn't touched by any of the code that anything's going through. So we're not going to change the behavior of this URL based on the change that we made. And so that analysis is kind of sloppy, but it runs really, really quickly. And so again, it kind of gives us a quick look at, here's what's new. So we know this is new, and presumably it's never been tested. But of the other stuff that has changed, here's the stuff that we have a reason to believe may have changed. There may be others that we may be over-reporting.
So like if you have a DevOps program, couldn't you use the percentages to have your SLAs, or at least some type of, if you're at a 5% or 10% look at?
Yeah, and I want to believe that percentage might be a metric that you would use. I'm not sure that like if you think about like that over time kind of compounds, where it's like, well, we're going to do a manual pen test every 10%. Well, you're going to do like day one you'll do a manual pen test, day two you'll do a manual pen test, day 5 you'll do a manual pen test. Like just as 10% gets to be a bigger thing as the application gets bigger. So I think that like rough URL count may be a slightly better metric for making those decisions, but that may or may not. Again, we've got the data, and that's kind of what we're playing around with, is to try to figure out like what are the good ways to drive this policy stuff, and that's what we came. And that like when I talk about the decision making, that was the thing that came out really quickly. Is like, okay, hey, our view is you can set a policy as no cross-site script, or no highs, or no cross-site scripting. And the immediate feedback from the development teams was like, no, because we've got a bunch of cross-site scriptings. We got some sort of a exception, and like those aren't going to get fixed for some amount of time. But again, what is politically possible, or it's one thing to say like, okay, I realize you don't want to shut down development for 3 months while you fix all this stuff, but can we at least agree that we don't want to knowingly introduce new vulnerabilities, right? Like that's a little harder to be on the other end of that conversation and be like, no, I need the right to introduce new vulnerabilities, right? So much as, if you look at like, again, so, looking at like raw URL count, looking at like percentage of attack surface that changed, those are some new, that's data that we didn't have available before that may or may not be useful in crafting, in kind of crafting and figuring out like what's the best use of our resources as we roll this stuff out. Yes?
How do you extend this to IoT devices?
So the broader challenge, or like the high level answer to that is like, you need to understand the attack surface of the IoT device, and then you would, so like, for example, what the analysis we're doing goes in, and from a web standpoint, it looks for calls to things like get parameters, right? And so we're doing like rough semantic analysis to find calls for like get parameter. In an IoT environment, you might know that I've got my toolkit that says like get datagram or get whatever, or get message from whatever. So you would add checks for those calls, and just need to be able to represent that in you'd have to know, well, this is how my IoT device gets data from the wall socket it's plugged into, or whatever that might be. And so that's really what you need to do, is understand for a given language and framework and APIs, this is how you pull potentially tainted information into this, and then that goes into your attack surface. And with IoT, it's trickier because you're like, well, hey, this thing talks to Zigbee and Wi-Fi, and and it has like buttons on the front or whatever. So, but again, that's what you would look and say. Again, from a threat model standpoint, where are the trust boundaries that people can cross? When I take that trust model and overlay it on the technologies and the toolkits that we're using, what are the API calls that are responsible for those, for things crossing those attack surface boundaries? Add those to the, add those to what you're detecting, and then that's, then you can presumably just like feed that straight in. Although I'd have like right now this is a little centric, web app centric, and then it's looking for like parameters and get and post and stuff like that. So, great. Anything else? All right. Well, thank you guys very much. Appreciate everybody coming out and maybe assisting.